For decades, manufacturing has been ruled by a simple law: economies of scale, produce more, and your unit costs fall. It's the logic that built global factories, sprawling supply chains, and the consumer world we live in. But additive manufacturing challenges this orthodoxy in a profound way. In AM, the cost per part when producing one part looks remarkably similar to the cost per part when producing 100. The old rule that bigger batches are always cheaper no longer holds. That's why we need to shift our focus. The real economic story of AM isn't about scale, it's about scope. It's about the ability to produce many different, complex, customized parts without paying a penalty for changeovers or tooling. It's about hybrid systems that blend additive with traditional methods, and it's about digital integration, distributed manufacturing, virtual inventories, and the rise of data-driven supply chains. Today, we'll stay on the manufacturing side of AM economics. In other episodes, we dive into certification, material strategy, and policy frameworks, the other pillars shaping adoption. You'll find those linked in the description. In this episode, we'll explore three themes. First, how AM reshapes the relationship between economies of scale and economies of scope, with real data on where the break-even points actually lie. Second, when AM makes sense as a production tool, and when it doesn't, using counterintuitive case studies from aerospace, defense, and beyond. And third, how the future will be defined by hybrid processes and digital integration, creating a new manufacturing logic altogether. Let's start with the basics and quickly move beyond them. In injection molding, die casting, or stamping, the first part off the line is ruinously expensive because you've sunk thousands, sometimes millions, into tooling. But by the time you've produced 10,000, the cost per unit collapses. Economies of scale dominate. Additive manufacturing works differently. Once the machine is calibrated and the powder loaded, the first part costs about the same as the 100th. There is no tooling to amortize. The cost curve is flat. That means AM cannot compete with molding or casting when volumes climb into the thousands. At that point, traditional methods always win. But here's where the economics become interesting. If you model the cost curves, the break-even point between AM and traditional methods sits much lower than many assume. For certain titanium aerospace brackets, studies have shown the crossover around 350 to 500 units, depending on post-processing intensity. For smaller, less complex parts, the break-even may be closer to 100 units. These are not back-of-the-envelope numbers. They come from detailed cost modeling that considers machine time, labor, energy, material efficiency, and finishing. And material efficiency is crucial here. Traditional subtractive methods can waste up to 90% of raw stock, especially in aerospace machining where a billet is milled down to a slender, optimized shape. AM, by contrast, uses only what is needed layer by layer, with unused powder often recycled. This alone can tilt the economics when working with high-value alloys. Scope is the other side of the coin. In AM, complexity is free. Making a component twice as intricate does not double the cost, and diversity is free as well. Printing 10 different parts together in the same build takes no longer than printing 10 identical ones. No downtime, no retooling, no changeovers. This is the essence of economies of scope, the ability to deliver variety and complexity at little or no penalty. So the old equation, produce more to save more, is replaced by a new one, produce smarter to save more. And remember, these curves bend even further once you account for qualification and inspection costs. We unpack that in our dedicated certification episode. Now let's test this against reality. Where does AM make sense today, and where does it not? The obvious place to start is prototyping. Here, AM is unchallenged. Being able to move from digital model to physical part in hours changes the rhythm of product development. Engineers can test, iterate, and fail fast without the inertia of tooling. For design-driven industries, AM is mainstream at this stage of the cycle. But prototyping is not the end game. Consider aerospace. This sector has been one of the earliest adopters of AM for production. Why? Because the economics change when performance and life cycle costs are factored in. Take GE Aviation's famous fuel nozzle. Reduced from 20 parts to 1, 25% lighter, 5 times more durable. The part itself is expensive to print, but the long-term savings in fuel and maintenance dwarf the initial premium. Similarly, Boeing's use of AM for titanium parts has saved millions per aircraft. These are not niche experiments. They are production programs delivering measurable returns. Now let's move to spare parts and decentralized production. This is an area where AM often makes more sense than people expect. Stocking spares is a hidden economic drain. Capital tied up in inventory, warehouses full of components that may never be used, and long lead times when parts run out. AM enables the idea of a digital warehouse. Parts stored as files, printed on demand where and when they're needed. Airbus has done this for cabin components. Defence forces have trialled it for vehicles in forward operating bases. Here, the per unit cost may be higher than a mass-produced spare, but the total cost of ownership, when you count storage, logistics, and downtime, can be lower. And yet, AM is not a panacea. There are clear limits. Machines are expensive to buy and run. Powders are costly. Build rates remain slow. A metal part might take 20 hours or more. Post-processing can swallow 15 to 30% of total production cost. And qualification is a hurdle that cannot be ignored. Aerospace firms spend millions certifying AM parts, creating rigorous protocols for each design and even each machine. For simple, high-volume components, none of this adds up. Here's a counterintuitive example. Automotive firms explored AM for lightweight brackets and heat exchangers. Technically, the results were impressive, but economically, the qualification effort and per-unit costs simply outweighed the gains at scale. Projects were shelved. It's a reminder that AM isn't better by default. It must be applied judiciously. So the picture is nuanced. AM is not a universal production tool, but a selective one. It thrives where complexity, customization, or availability are critical. It fails where uniformity and sheer volume are paramount. The challenge for professionals is to identify precisely where it adds value and where it does not. And again, qualification costs are a big part of that story. See our certification episode for how they reshape the economics. If the present is nuanced, the future is hybrid. Imagine a machine that prints a near-net shape with all the internal complexity of AM, then switches seamlessly to machining the critical surfaces to exact tolerances. Such systems already exist. They allow manufacturers to capture the design freedom of AM without sacrificing precision. Hybrid repair is another frontier, adding material to a worn turbine blade or tool, then machining it back to spec, rather than replacing it outright. Economically, this changes the logic of maintenance. At the same time, throughput is improving. Multi-laser systems are cutting build times significantly. Larger build chambers and smarter software are optimizing part placement and reducing waste. But even with these gains, AM is unlikely to match the raw output of injection molding or stamping. That's why the hybrid model is so important. AM does what it does best, and conventional processes do the rest. The other frontier is digital. AM is, by nature, digital first. That makes it an ideal candidate for integration into Industry 4.0. We're already seeing early examples: digital inventories replacing warehouses, distributed networks of printers producing parts on demand, and digital twins simulating entire builds in real time. Siemens, for example, has developed twin systems that adjust process parameters on the fly to prevent defects, effectively moving towards in situ certification. And think about supply chains. Traditional logistics are long, brittle, and vulnerable to disruption. Distributed AM hubs directed by digital demand signals offer resilience and responsiveness. Add sustainability into the mix: less waste, shorter transport routes, more efficient use of materials, and the economic case strengthens further, especially in a regulatory climate increasingly focused on carbon. So the next logic of AM is not replace the factory, it is embed within the factory. It is not additive versus traditional, but additive plus traditional plus digital plus sustainable. And to see how policy and standards are catching up with this digital shift, you'll find our dedicated episode on policy, standards, and the future of AM adoption in the series. The core economic lesson is this: additive manufacturing doesn't win by scale. It wins by scope. It wins when you need complexity, customization, or immediacy. It loses when you need simplicity, uniformity, and millions of units at the lowest possible cost. But the boundaries are moving. Hybrid systems are closing gaps. Digital integration is creating entirely new forms of value. And sustainability pressures are pushing us towards models where local, efficient, and on-demand production is no longer just desirable, but necessary. For professionals in AM, the opportunity is to see clearly where the technology works today, where it does not, and where it is heading tomorrow. To be realistic about its limits, but strategic about its integration. And above all, to recognize that the economics of scope and hybrid futures represent not just a shift in cost structures, but a shift in manufacturing logic itself. If you've enjoyed this deep dive, do subscribe. Each episode in this series unpacks a different facet of metal additive manufacturing, connecting technical detail with strategic insight. For the true cost breakdown, see the true cost of AM. For one-offs under regulation, see one-off on demand. For materials choices and AM-specific alloys, see Materials Spotlight. And for the policy and 2030 outlook, see Policy, Standards, and the Future of AM Adoption. Subscribe now to stay ahead of the curve, because in this field, understanding the next logic of manufacturing isn't optional, it's essential.